we are talking about application of Fourier transform. So in this lecture also we will continue. Specifically we are going to talk about filter response. So let us recap what we have done till now. Okay, in the last lecture and a couple of previous lectures, we saw how the Fourier transform method can be employed to evaluate the transients in a network. Essentially, when we wish to find out the transient behavior of a network, it is generally after switching operation. You have some Vs and you have a switch, and the switch is closed at t equals 0. You have some inductors, then maybe capacitors and resistors like this. So when t less than 0, that times the circuit may have some initial stored energy. Okay, so some initial current through the inductor and capacitor, some initial charge across the capacitor like that. Okay, so let us assume that some excitation function is introduced in the circuit at exactly t equals 0, and we wish to find out the response of the network following the switching operation. That means what? T greater than 0, we would like to find out the circuit operation. Okay, so we should make two assumptions in this case. The first assumption is, first of all, the first assumption is, first of all, the network is initially relaxed. That means it has no initial energy stored in the network. In other words, capacitors are initially uncharged. And inductors carry no current. That's what we mean by initially relaxed. This assumption of the network being initially relaxed does not entail any loss of generality, because if indeed there are initial charges on the capacitor or initial currents in the inductor, they can be replaced by equivalent sources. It's not a big deal. So these equivalent sources can be considered to be additional excitations in addition to the input function Vs. Okay, so these all brought together by the principle of superposition, and to evaluate the response to the various excitations and adding them up to find the total resolution. Therefore, we shall assume that the network is initially relaxed, and we are interested in finding out the response of the network following the switching of an excitations at t equals 0. And the second assumption that we like to assume is that we will make that the natural response of the network is 1, such that it dies down to negligible portions in course of time. Okay, that means complementary function that we are not going to consider. At when t equals 0 and t greater than 0, the contribution of complementary function will be negligible. Okay, and this is common to most networks that we deal with, particularly dissipating networks, because when you find out the complementary solution, then you will have e to the minus some alpha times t. Okay, when t becomes greater than 0, then this part will goes to 0. Okay, and this one does not, this part exponent part does not seriously disturb the generality of the situation. However, the Fourier methods can also be applied where the natural frequencies of the network have 0 real part. In other words, they are sustained natural response, oscillations, sinusoidal oscillations, or a DC component. But the analysis becomes a little more complicated, but we will avoid situations of this type in this course. That means we will assume that the natural response decays with time. Natural response decays with time. So therefore its contribution is very less, no need to consider. Under these two assumptions, when we have an excitation switched at t equals 0, you are connecting the input at t equals 0, we expect the response also to be 0 up to t less than 0 or up to t equals 0. because the network is assumed to be causal. Therefore, any excitation that is applied at t equals 0 cannot produce a response prior to that. So, we expect the response to be 0 up to t equals 0 and then become non-zero from t equals 0 onwards. So, response equals 0 for t less than 0 or less than or equal to 0, and the response is not equal to 0 for t greater than 0. That means positive t. Now, the Fourier method tells us that any such excitation function can be split up as the sum of tiny sinusoids. That is what we said. X of t contains infinite number of sinusoids. Please refer the previous lecture. Infinite number of sinusoids. Tiny sinusoids. Infinite number of tiny sinusoids. Okay. All the sinusoids starting from t equals minus infinity onwards and going up to t equals plus infinity. Now, each one of the sinusoids produces a response which can be evaluated using the steady state sinusoidal circuit theory methods, that is using the frequency response techniques. And then all these responses which can be added up to find the total response. So, sum of the steady state responses is what we obtained through the Fourier integral approach. If you recall, x of t is equal to 1 over 2 pi integral of f minus infinity plus infinity x of j omega, then e to the j omega t and dt. There are many tiny sinusoidal inputs, and now you sum them up, then your y of t is equal to h of j omega times x of t, provided that when x of t is in the form of e to the j omega t. Okay. So, we observe that if there are any natural response terms produced at t equals minus infinity, at that time where excitation starts, all the sinusoids starts from t equals minus infinity, and all these natural responses will decay to negligible portion by the time t equals 0 arise. This is the period in which we are interested in, like t equals 0 to t greater than 0. This is the period we are interested in. So, we are interested in finding out the behavior of the network from t equals 0 onwards. So, we do not bother what happens before t equals 0. Okay, that means the natural response terms which might have emanated at t equals minus infinity, but it dies down, okay, would have decayed to negligible portions when we come to t equals 0 onwards. But the sum of steady state response, the sum of the steady state response include transient terms, it includes natural terms, that is complementary solution, then natural response starting from t equals 0, that is particular integral. So, the steady state responses will add up to 0 up to t equals 0, and from t equals 0 onwards, the response that we get, that is the total response that we get, include not only the forced response but also the transient response. Okay. Now, let us take a second example to illustrate the application of the Fourier theory to a network or a system which is characterized by its frequency response h of j omega. Okay. So, now let me take a filter, filter network, and see how the Fourier theory can be applied to this filter network. So, example. Okay. Now, let us consider an ideal low pass filter, LPF, low pass filter. Low pass filter means it allows the frequency up to a certain frequency, 0 to certain frequency. So the filter is like this. It allows 0 to some frequency, let's say omega c. Here c indicates cutoff frequency, cutoff angular frequency, omega with magnitude 1, and this is the h of j omega and magnitude. What does it mean? It passes the frequency without any attenuation and without any amplification also. It passes the frequency from 0 to omega c as it is, no disturbance. Okay, therefore you have a low pass filter. This is your input, and let me say this is your output y of t, and the input is x of t. Okay, so the x of t may contain frequency from 0 to somewhere else, but in between 0 to omega c, what are the frequency component present here? These frequency components are not disturbed by the low pass filter, but these frequency components from omega c onwards completely eliminated by the low pass filter. It will not allow to pass through this filter, and this filter is very, very important, especially this filtering concept. In communication we use this filtering concept repeatedly, because we want to select a particular channel or pass it on a particular channel and reject all other channels, so that you may have something called a band pass filter. That means it passes a band of frequencies which you are interested in, and remaining frequencies all are rejected. Okay, so this is called ideal low pass filter characteristics. Okay, so why is it called ideal? I will let you know. I will tell you in a few minutes. Okay, so the frequency response function, if you write down h of j omega can be considered to be 1 if the frequency, angular frequency mod of angular frequency is less than or equal to omega c, and 0 otherwise. So this is a kind of response function that we have. Now under these conditions, okay, this is mod of h of j omega, and this is my h of omega. Okay, now what is my y of t, or I mean output? Y of j omega is equal to h of j omega, you take magnitude of that, multiply by x of j omega. What is x of j omega? X of j omega is the Fourier transform of input x of t. Now in this case, let me consider x of t is equal to u of t. If it is u of t, then what will happen? Then x of j omega is equal to 1 over j omega plus pi times del of omega. You can substitute back in this expression. So this is going to be h of j omega, you take magnitude, or let us not consider magnitude here, let it be as it is. Okay, times 1 over j omega plus pi times del of omega. This is what your y of j omega, Fourier transform of the output. Now we wanted to know how does it look like in the time domain. So what you do, you take the inverse Fourier transform of this, you will get y of t. So this is inverse Fourier transform of this whole thing, h of j omega multiplied by 1 over j omega plus pi times del of omega, like this. Okay, take the inverse Fourier transform of that. So you just write down the inverse Fourier transform formula, that is Fourier integral 1 over 2 pi integral of, the limit is minus infinity to plus infinity, h of j omega multiplied by 1 over j omega plus pi times del of omega, then e to the j omega t times d omega. Now we are integrating with respect to what? Omega. and we know that h of j omega vanishes when omega exceeds omega c. That's what we said. Omega c has a filter characteristics of 0 magnitude, right? So this is what we have said. It exists up to as long as omega is less than omega c, mod of omega is less than omega c. Therefore this integral limit also changes. Okay, so this h of j omega vanishes when mod of omega is greater than omega c. Therefore we need to carry out this integration between the limits minus omega c to plus omega c. 1 over 2 pi minus omega c to plus omega c, because outside the integral vanishes. Within this interval, what is the h of j omega value? It is 1. Look at here. That's how we defined it is 1. So 1 times 1 over j omega plus pi times del of omega multiplied by e to the j omega t and d omega. Now you break this integral into two parts, 1 over 2 pi minus omega c to plus omega c d omega by j omega already I wrote it, plus pi you can bring it outside. Therefore 1 over 2 integral of minus omega c to plus omega c e to the j omega t times del of omega and then d omega. I'm sorry, I forgot e to the j omega t here. Okay, now 1 over 2 pi integral of minus omega c to plus omega c. This e to the j omega t I can write as cos omega t plus j times sine omega t whole divided by what is that, j omega times d omega, plus in this 1 by 2 and this multiplication theorem substitute omega equals 0, then that becomes minus omega c to plus omega c, then e to the 0 1, so del of omega times d omega. Recall the property, x of t times del of t is equal to x of 0 times del of t, then x of j omega times del of omega is equal to x of 0 times del of omega. The same property we used here. So instead of, if you multiply by del of omega, you substitute omega equals to 0 in this expression, and by definition this is the area of the unit impulse, so which is equal to 1. So you will get 1 half plus 1 over 2 pi, then again I have two parts here, I can break this into two guys. Okay, so integral of minus omega c to plus omega c cos omega t by j times omega d omega plus 1 over 2 pi integral of minus omega c to plus omega c, then j times sine omega t divided by j omega times d omega. Now what is this function? Cos is even function and j omega is odd function. Even by odd becomes odd, therefore you are integrating over symmetrical limits, therefore this guy becomes 0. So 1 by 2 pi plus 0 plus this j and that j will get cancelled, 1 over 2 pi. Again sine is an odd function, the denominator also you have an odd function, odd by odd it becomes even. So minus omega c 2 plus omega c sine omega t by omega times d omega. So whenever you have an even function you can change the limit, 2 times you can write, so plus 1 over 2 pi times 2 times integral of 0 to omega c sine omega t by omega times d omega. This we already calculated. Okay, this is something called sine integral, right? Please recall this one, sine integral. How do you denote the sine integral? Si of the argument parameter, sine Si of omega, omega c omega t, and The upper limit is c, therefore I put a c here, because I can write this as follows, okay, like 1 by 2 plus 2 will get cancelled, 1 by pi 0 to omega c sin omega t by omega t times d of omega t. Like this I can write. I mean, you introduce t in the numerator and t in the denominator. Now this can be thought of sin theta by theta and d theta, and once you have taken this as theta, then the limit will be omega ct. Omega becomes omega c and omega t becomes omega ct. Okay, so this whole thing becomes psi of omega ct. So your y of t is equal to 1 by 2 plus 1 by 2 psi of upper limit omega ct. Now if you evaluate this, this is the constant, that is this 1 by 2 is a constant, a DC term. As far as this is a DC term. As far as this sine integral is concerned, if you recall that sine integral will have a characteristics like this. It increases like this, and then it reaches some peaks and then keep on oscillates and settle down, and the settle down value is what? Pi by 2. Similarly, in the negative axis also it comes like this. Like this, it settles down to a value minus pi by 2. Okay, minus pi by 2. Okay, but this is multiplied by 1 by pi. That means this quantity, this pi by 2 multiplied by 1 by pi, and this also multiplied by 1 by pi. So pi will get cancelled. So eventually it is minus half, and this point is plus half. Okay, so and therefore so it goes like this, then here also like this. So this point is 1 by 2 and this point is minus 1 by 2. What is this function? 1 by pi times sine of psi of omega ct. Now with this we are adding 1 by 2. So add 1 by 2 with this. If you add 1 by 2, then this will be equivalent to, you are adding the constant value 1 by 2. Then what happens? This half, let me draw here like this, 1 by 2. Now here this point is minus 1 by 2, and here this is plus 1 by 2. If you add this guy and this guy up to t equals 0, then this portion will shift to 0th line. Okay, so therefore it comes like this, settles down in the 0th line. Okay, and then it reaches and it comes to one line now. This point is 1 now, and this one is 1 by 2 plus 1 by 2 sine integral of omega ct. That's it. This is how it looks like this. So finally your y of t is equal to 1 by 2 plus 1 over pi sine integral of omega ct, and this looks like this. It reaches and settles down, okay, with the value of 1. Then here it oscillates between like this. For this is t equals 0 line, and this is my t. This is y of t. Okay, so this will be the response for unit step function. Okay, response of the ideal low pass filter. Okay, for a unit step input, you have ideal low pass filter. You are giving the input x of t, that x of t is unit step. That means what? You are applying the input at t equals 0, and before t equals 0, what is the input? 0, right? In this range, what is the input value? Input equals 0. This is my x of t. Your input is 1 exactly when t equals 0. But on the other hand, if you look at the function, it has certain output before the application of the input. Before you apply the input, there is some output. Okay, you have a unit step input here at t equals 0. The output will be like this. You have some output before t equals 0. So, and depending upon the cutoff frequency omega c for the low pass filter, if you make the omega c larger and larger, this oscillation, okay, this portion becomes smaller and smaller, becomes more closer to the unit step function. So, if omega c becomes much larger, then what happens? The curve, instead of going like this, it goes like this, and instead of overshooting, it slowly varies like this. Okay, more and more closer to the step function. That means oscillations will reduce. These oscillations will reduce. Okay, between finite value. So, the more the cutoff frequency of the low pass filter, that means the greater bandwidth for the low pass filter. It becomes closer and closer to the input. Actually, the excitation function is 0, as I said, up to this point. And after t greater than 0, greater than or equals to 0, the response is, the input is non-zero. Therefore, we expect the response to be non-zero after t greater than 0. But what happens here is that even before the excitation is applied, there is a response. See, the response is slowly oscillating like this. Even before the input, there is a response. This clearly shows that this is a non-causal system. Causal means what? We know the definition. Okay, so this is the non-causal system, and which means physically this is something which we cannot expect to achieve physically. Therefore, if somebody comes and says like a ideal low pass filter, then that ideal low pass filter cannot be realized physically. And therefore, an ideal low pass filter that we are talking about here with let's say this type of characteristics, can only be approximated. It can never be realized. Okay, so if you have this kind of characteristics, it can be approximated. Approximately you can realize, but exactly you cannot realize. That's what we mean by. So it can never be realized in practice, because we believe that no physical system can give a response even before the excitation is applied. See, without giving the input, how can you expect a system to give the output? It is not at all possible. So this is non-causal situation, and this is one way of showing that an ideal low pass filter of that particular characteristics is not achievable in practice. Okay, and what can do is modify these characteristics in such a way that this portion of the output is avoided. That means if all low pass filters that we can build in practice cannot give this kind of response, it can give only response from t equals 0 onwards. So that means what? For practical system output y of t, it should give 0 output up to t equals 0, and then it can start to give some kind of output. So this is a practical low pass filter. On the other hand, if you have a filter like this, This is impractical, or we can say non-causal filter. So non-causal filter you cannot realize. However, my point in showing this example is that the Fourier transform methods can be applied to network to characterize in terms of frequency response as here. So Fourier transform is a very convenient tool in such a situations. Okay, so let me stop at this point. In the next lecture we will talk about sampling, an important application of Fourier transform. Okay, so in the next lecture we will talk about sampling. Let me stop at this point. Thank you very much.